Good morning, COMP1511. I'm going to move my face up to the top right corner. How are we all doing this morning? Hope everyone is enjoying their Friday so far and looking forward to chilling out for the rest of the weekend, hopefully. Or, I don't know. It's like, hey, that guy just gave us an assignment, now he's telling us to chill out. Yeah, so either chilling out of the weekend or fulfilling ourselves with some wonderful work that we're going to put into the assignment. Sorry, I can't help but laugh every time I say stuff like that. Having said that, we did write the assignment with a bit of sometimes when you're creating things for people to do, you go, what can we do that would be like a little bit fun while still learning about this stuff? So, I mean, hopefully people like when they see the things that they get to do with the assignment and they see the stuff you can create with it, will be at least a little bit interested in it. Sean saying, I wish this was the only assignment I had to do. It kind of happens, I guess. The one thing that we always find is that all of us lecturers look at the term and we go, okay, so we're teaching 9 weeks out of 10. We're probably going to have 2 assignments in this term, which means we won't have anything due early. But we will probably have something due sort of midway or just after midway through the course, and something else due at the end of the course. And so it turns out that all of our assignments end up with the same due date. It would be interesting if we could find a way to stagger when all the due dates were, but there's no way that we can even know what subjects everyone's doing. So if we wanted to, we could try to cater to some of the core people who are doing, say, maths and computing at the same time or something, which I know is a huge overlap. But then even then, we don't have any guarantee that everyone's in the same term. We could move all our assignments around and sort of compromise the teaching in any one particular course for it, and then not even actually help that many students at a time. So it's always rough. So I always end up knowing that when my assignments, which are always week 6, week 10 due dates, I kind of know that there are going to be other assignments at the same time, but at the same time, I can't really do that much about it, because if I shift the assignments 1 week in either direction, then it changes what content is in them, and it makes it really awkward. So either it bunches up more stuff at the end of the course, or they come too early and there's not enough content to actually do the assignment. So things get a little weird, and I do apologize because I know the situation, but there's not much I can do to change it, unfortunately. Sean saying, yeah, I should just drop everything else. Yeah, and so I hope that, as Miguel's saying, there's so much cool stuff you can build into it. I hope everyone who's looking at the assignment so far is seeing that it's the tip of the iceberg. There is some stuff that you're doing with the assignment, but what it might also be doing is opening up your eyes to the possibilities of what programming is. When you realize how much control you have over the computer once you learn these basics and get over the starting point of how do I just barely communicate with the computer, you suddenly realize that this tool has so much potential, and we've barely scratched the surface at this point. So hopefully it kind of inspires some people to think about what they could create in the future with computers. Okay. Gary-chan, just enroll in COMP1511 3 times. I'm not sure that's how that works, because the only way the university will allow someone to enroll in the same course more than once is if they don't pass it the first time. So, I don't know if that's exactly the way that you want to do things. Also, if you are doing a full computing degree, there are courses that follow on directly from this one that build on and continue in the same vein. So maybe it's not necessarily about doing 1511 multiple times, but seeing what follows from 1511. Okay, let's launch into the lecture itself. What did we learn last lecture? So when I say last lecture this time, I'm not talking about yesterday's live stream. If anyone's interested in yesterday's live stream, the YouTube playlist has yesterday's live stream. I've also uploaded it to our Moodle Echo 360. So if you're not able to access YouTube and you're using the alternative download, the content's there as well. So I'm just mirroring the content in two places in case people need it. So on Tuesday, we were talking about functions and libraries. So I'd introduced functions and arrays initially, and Tuesday was us expanding on both of those topics in a little way. So the way that we were looking at functions was we were talking about how to include libraries. And this isn't really new as such. This is more of an explanation of something we've been using since the very, very first program that I showed you. When I showed you the very first program, we were using the standard input-output library right from the beginning. Because it's very, very hard to teach people anything about programming without having some kind of output coming to the terminal so that people can read what's going on. Morning, Shrey. We'd been using it the whole time, but now we had a bit more of an explanation of exactly what it was. And we showed a few other C standard libraries that you could get into if you wanted to. I said then that we were going to have more libraries that we were using. As we go on in the coming weeks, we will be basically every new topic, not exactly every new topic, but most of the new topics we're creating, we're going to be looking at which libraries will support us in doing our work. So they become a fundamental part of what we do in programming with C. It's the idea of not reinventing the wheel. We may be doing cool things with the wheel that people haven't done before, or learning new things that we haven't learned before about it. But when someone's already done something to do a simple task for us, there's no reason for us to do it again. So printf and scanf are good examples of that. We also looked at multi-dimensional arrays, which is containing an array in an array. So if we've got arrays in arrays, that means each element of our array actually contains multiple normal elements. I've got some diagrams I'll skip to in a second. Maximilian is saying, Mark, could you introduce us to the different computer science majors, maybe in week 6, I think you're saying? Most of us will have electives and have no idea what major subjects to pick. I may or may not be able to give you advice on that, but we can talk about that later. I think it's actually better to talk to either anyone who can help you with enrollment in the programs, the student nucleus or things like that, or have a chat with the people at CSESOC about that. Tom says he's written an article about that, so there's some information there already. I'm actually, it's weird, right? Because you tend to look at your lectures as this kind of fount of knowledge and things, but in terms of actually how the courses, the programs and the degrees and the majors and stuff actually work within UNSW, I'm not actually a very good person to talk to about that, because I focus on teaching this one course, but I haven't actually looked that closely at the content in the other courses, because I'm not someone at CSE that we call a program director who might know that kind of thing. So each lecturer knows a whole lot about one particular field, but we don't necessarily know about all the different fields and all the different ways you might structure your degree. So have a chat with some other people about that. Yeah. Okay, so what are we covering today? So today we are going to get a little bit closer to our computer than we have before. We're going to have a look at what computer memory actually means on our computer, and then we're going to look at a new variable type. And this is a really, really interesting variable type, because all of our variables up until now have been storing some kind of information. And so they've been plain information, as in just a number that just has some kind of value that we're going to use. We're going to do some maths with it or something. Or in CS Paint, the numbers that we're storing are colors on a canvas. In a lot of those dice rolling apps that we've been playing around with, the numbers were all values on a die. Now we're going to start using values for our variables that are positions in our computer's memory that we can look at. So we're actually going to use variables to access other variables. So you can nearly think of the pointer, which is the variable that we're going to describe today, as a meta variable. It's a variable that allows us to get access to other variables. And initially, when you look at it, it's sort of like, why do we need access to other variables when we have just the name of the other variable already? But once you get a little deeper into it, it starts to open up a whole lot of extra possibilities. And so what I'm going to do is introduce what they are and the basics of how they work, how we can integrate them with functions, and we're going to continue our work with functions today. And over the next couple of weeks, I will start opening up the possibilities of what we can do if we have the ability to kind of reference another piece of memory in the computer from somewhere in our code. I'm being vague about it for now because until I give you some of the background and theory, you won't fully understand everything that's going on here. But as I go through this, we'll get a bit more information about this. And I think for a lot of people who may have studied some programming before, this is the point where you want to actually really start paying attention. So up until now, everything that I've taught has been something that has an analog somewhere else in most other programming languages. Those are the real fundamentals of programming. And now when we get to this point, this is where C locks into the fundamentals of what a computer is, that most other programming languages will gloss over. So this is the point where we start playing with, it's kind of like a lot of programming languages sit at this level, and the computer's down here at the, it's physical, and it just does its bits and pieces with bits and bytes and stuff. And most programming languages sit up here, and the operating system handles all this other stuff. C dips down into there. So C can dip down in there a bit closer to where the hardware is and what it's doing. And most other programming languages won't do that. So today we're going to start getting into that. Okay, bit of a recap. I mentioned this already in that opening slide, but we just want to go through a little bit of a recap of what we've learnt up to this point, because I'm probably not going to be introducing libraries again, and I'm not really going to be introducing multidimensional arrays again. So a little quick recap on those. So the functions we can use from C standard libraries, they are going to be included in batches in our code, basically using the hash include function. The hash include you can nearly think of, and your compiler will see it very similarly to this, as you can nearly think of it as taking another file. The other file has all this information about C and copy pasting it into your code where the hash include line is. So you can say, I'm kind of replacing the hash include line with this entire file, standard input output.h, like this entire file, or standard lib.h or math.h. And as we go on, there's going to be more h files that we use. So the h file is a particular form of C file. We're going to look into that later as well, but for now you can think of it as a kind of a C file that gives us access to a library. So once we have the hash include there, we will be able to use all of the functions were written in that h file. So for example, the standard input output.h has printf and scanf in it, but it also has way more than that. So we're actually going to get access to a whole suite of things that can do input and output to the terminal. I said we'll see more of these today, but I'm not sure if we're actually going to do that yet. Yeah, because I don't think I'm actually introducing any new libraries today. I wrote this because I was thinking that we were going to use some standard library stuff today, but I'm not sure if we necessarily are. Multi-dimensional arrays. As we've seen, arrays are a type of variable. Basically, anything that we can declare that's going to store some information for us is a variable. An array happens to be a variable that stores a larger chunk of memory that can have multiple of the basic variable types in it. But it's not just the basic variable types that can be stored in an array. Any other variable can be stored in an array, which means an array being a variable, an array can be inside another array. So an array of arrays means that, say, this is one of the arrays here that has 3 elements in it. Each element of this array is another array with 5 elements in it. So with this kind of two-dimensional nature, we can then start to store a grid of information like this. And this is the kind of thing that we're using in assignment 1, sorry. Actually, we're not using arrays at all in assignment 2. In assignment 1, we will be using this to store a canvas on which you can draw things. A bit of code for accessing what is in an array. We have the normal array declaration, and then we put another set of square brackets and another number there, gives us this two-dimensional array. If we wanted to do a three-dimensional array, we do another set of square brackets and a four-dimensional array, and so on and so forth, until you as a human are no longer able to understand exactly what's going on with those arrays. Izzy, this is a tough question. Izzy's asking, what is the best way to find out about commands in a library? You can definitely do it a couple of ways. You can look up the manuals in Linux. So you type in man, M-A-N, and then the library, like standard input-output.h, stdio.h, and then it will show you a lot of things. You can also just search for that file name online on Google, and then there will be tutorials that come up, or just reference material that says what's in it. The downside of that is you just get a whole lot of reference material. In terms of actually learning the functions in the libraries is a matter of practice, because it's kind of like I give you a toolbox, and the toolbox is full of all these different shaped tools, and you don't really know what all of them are for yet. So if you just look at them and you pick them all up, you can kind of guess what some of them are for. But knowing what they're for becomes a matter of like trying to figure out which problems you want to solve with each one. So it's sort of something where you will build up a knowledge of them as I teach you the couple of the different things that you can do with the libraries. And then you'll hit a certain point where you know enough about the libraries you can start teaching yourself about the others. But I think that for the moment, knowing what's in all the libraries and how to use them starts off with just using the ones that I've taught you, and then you sort of expand as you look around and go, oh, there's other functions in there that do similar things but a slightly different way, or they do the same thing for other variable types and things like that. So I think at this point, going through all the libraries and trying to read all the functions that are in them might be more confusing than it's worth. But by the end of the course, I think you'll be in a position where you could actually just look up reference for the standard libraries and say, okay, these are things I can use, these are things I don't have to use. It's one of those confusing things. So I think the hardest thing about it is potentially writing code that you didn't have to, that one of the libraries would have done for you. But I think that's a matter of experience, and you've got to kind of get into it before you'll know exactly how to use them. Oh, Shrey's got one of the links there. Yeah, that's one of the links that I use a fair bit. There's this thing called Tutorials Point that I've seen, and it's one of the first things that turns up when you Google reference for C for things. It's, yeah, as I said, you'll see what's on offer, but you won't necessarily fully understand everything that's in it yet, which is fine. You know, I can walk into a carpentry workshop and I can identify, I don't know, 10% of the tools there, and I've used maybe 10% of that. But I understand that all these other things exist, and with time and learning, I could figure out how they all work. And I think that's the same thing with the standard library. You look at them all and you say, oh, printf scanf, I know exactly how that works. Standard input-output library, there's a whole bunch of other stuff in there. I don't exactly know how all that works, but I could extrapolate some of that from what I know from printf and scanf. And then you look at another library, like the standard library.h has a lot of weird arcane stuff in it, and you say, okay, I'm not going to touch any of that stuff yet because I don't know exactly what it does, but I will think about the fact that maybe in the future, as I get more expertise, I will start to learn more and more about that, and then I will be able to take that knowledge I have and apply it to these other libraries and learn how they work. So I think it's kind of like a bit of a time and practice thing, in a sense. Okay, so some code there for 2D arrays. Remember, when we're working with arrays, the square brackets are the symbol of the array. So most of the time when we're using arrays, the square brackets will be involved. When we're creating the array, the square brackets allow us to determine what size the array should be. So this is, say, rows and columns of a 2D array. I tend to work in rows and columns all the time because it's easier to loop through it if we think of rows first than columns, even though that's actually the opposite of how maths coordinates work. When we're then using the array afterwards, so we can tell we're declaring something by the fact that there's a variable type there. Because there's a type, it means we're creating a new array. There's no type here before the word grid, so this is using something that's already been created. So when we use the square brackets on something that's already been created, we're accessing an individual value of that array. So in a 2D array, if we have two square brackets, we are accessing an individual integer. Well, if it's an integer array like this one. If we only use one square bracket, we would get a whole array. We'd get one of the rows of the 2D array like that. So there's different ways we can access it, and if we don't use any square brackets at all, we just use the word grid, we're giving the entire 2D array to something. So we can access the whole array, a single row of the array with a single square brackets, or with the double square brackets, a single element in the array. I'm not sure how handy that will come in the assignment, but it might. There's definitely going to be times, like even the basic sort of print out the whole canvas, you would give it just the name of the array, so it has the whole canvas in that function to do things. Are we going to... Yeah, I think we'll be doing a little bit more passing arrays into functions today. Actually, we're going to talk about some of the details of the back end of what's happening with arrays and functions. So today we're going to talk about memory. So we're going to talk a little bit deeper about all the memory that's on your computer. So talking about like random access memory mostly, which is the stuff that stores all the information on our computer while it's being used. So when it's not necessarily being used, when it's being stored long term, it's on our hard drive, and then when we start to run our programs, we copy it into our memory, and then we go back and forth to our memory, rewriting things to it and stuff like that. So when we think about our memory, I'm going to use an analogy that I like to use of like a kind of a neighborhood of houses, or you can think of it as an apartment block full of individual apartments. And the way that memory is organized on most modern computers is that each piece of memory is 1 byte. So each piece of memory is 8 bits of memory, which means it's unlikely that we'll ever be accessing anything smaller than 8 bits at a time. And actually most of the time we'll be accessing things that are larger than 8 bits. So it's kind of like every integer is 4 apartments. It's a very rich integer. So because a byte is 8 bits and an integer is 32 bits, it will hold up 4 of those bytes at a time, and then it will store its information in 4 of those bytes. The address that we would use to find that integer is the first one of those. So every apartment in the apartment building has an apartment number, and it's unique, and those kind of count upwards as you go through the building. And we're going to be using a similar thing in our computer's memory to access individual integers and doubles and even pieces of code and things like that. So the reason this comes directly after we're talking about arrays is arrays are very similar to this, where we're explicitly addressing individual elements by number. If we consider our computer's memory to just be one really, really big array, so it's a massive array. So on my computer here, it's a massive array that stores 16 gigabytes worth of information. So if I was looking at a really fundamental level, at some point that array has been declared to be all of my computer's memory, and then I can go into that array and change things, which means that every piece of memory on my computer, every byte out of those 16 gigabytes, so giga is trillion or quadrillion? I should actually look that up, but you know, it's so big that I don't really bother trying to figure out what the word name for the number is. So each one of those giga amount of bytes has its own individual address, and that's like the index into an array. So that means that if I know the number of a piece of memory, then I can go into that piece of memory and I can change it and things like that. And I know also that everything in my program is in that memory somewhere. So every variable that I create in my program exists in memory. Here's a bit of a diagram just showing the idea. So the address of each piece of memory is actually an integer. We're not going to use the integer variable type for it. This is me mathematically saying it's an integer, it's a whole number. But wherever something exists, so somewhere in my memory here, there's these addresses for each element of memory, and each element in this memory is some kind of information. So, oh, Miguel's done the maths for me. It's just a billion. So just a billion. So each gigabyte is a billion bytes. So we've got 16 billion bytes. So I've basically declared an array of size 16 billion. And that is my entire memory on my computer here. Every computer's got a different amount of memory on it. So this could have been 107,600 something thousand. You know, like it's just some massive number. And that will give us access to this piece of memory here. So what we're getting towards is the idea that if I can figure out what the address is of any particular variable that I have in my program, I will be able to find the piece of memory on my computer that actually stores the information for that variable. And so we're going to get to the point where we will start storing these addresses and using these addresses to find things. It actually has been happening under the hood while you've been programming so far with C, is that you've been working with variable names. And that variable name, when the computer compiles it, so when DCC runs on your code, it looks at that variable name and says, okay, human has this name for this. And the human has said, this is integer dice 1 total or something. I don't use those words to represent things, so I'm going to say every time the human says dice 1 total, I'm going to say memory location 106. And then when I see dice 1 total, I will go to that memory location, and that's where I've stored that integer. You know, so the computer's already been doing this kind of thing where it's saying every variable exists at a memory address somewhere. So a little continuation of this. I think I've already said everything about this. So each variable is a house or an apartment somewhere in this. And if we have the idea of what variable type it is, we know how many houses are being used for that variable. And if we know the address, we know where that variable starts. And so we have access to everything that we need to read the information from that variable. In our systems, in our modern computer systems, they're usually 64-bit computer systems. With 64 bits, we can address up to 2 to the 64 bytes of memory. And 2 to 64 is a lot higher than the 16 billion that I have, which means I have the ability to address all of the memory I have, and we're future-proofed against our computers getting more and more and more memory. Interesting thing for those of you who are doing the maths there on number sizes and how much memory we can address, check out what 2 to the 32 is capable of doing. So not that long ago, I would say, what are we looking at? Maybe about 15, 20 years ago, when we finished crossing over from 32-bit systems to 64-bit systems, it changed how much memory we could actually use. Yeah, Miguel's doing some maths here. 2 to 32 is only 4 gigabytes. I think it's actually even potentially less, right? Is it 4 gigabytes or 2 gigabytes? It might be that with the positive and negative possibilities for those numbers. Because I remember the old limit that we used to have Yes, yeah, Tom's saying 2 to the 31 is 2 gigabytes, because the old memory limit we used to have in the 32-bit era was that no single program could use more than 2 gigabytes of RAM at a time. So our addressing system was not capable of addressing more than 2 gigabytes of RAM at a time, so anytime you wrote a program that was bigger than that, it wouldn't run on a 32-bit system, which is why we're on a 64-bit system now. All they did was double the number of bits necessary for addresses in memory, and then doubling the number of bits meant we've now able to access, I think 2 to the 64 can nearly access all of the memory in all of the computers in the world. Like it's at that level, so we're probably not going to hit that scale for, a few hundred years or something like that. Miguel's saying, I know that most 32-bit programs can only do 2 gigabyte at once. You can actually patch them to use up to 4 gigabytes. Yeah. And I remember around the time, I think it was Windows 2000 operating system, they started being more careful with that. So before that, we had, I think the reason we had 2 gigabytes was 2 gigabytes were reserved for the system, for the operating system, and then 2 gigabytes on top of that for any individual program. And all the programs were sharing that 2 gigabytes as well. So you couldn't run too many different things at once. So fiddly era, and we're glad that that's over. And we're in the 64-bit era now, where we have so much address space that programs can grab different chunks of address space and still have so many numbers available to store their memory. Okay, so new variable type, something that we're getting into, which is going to be quite interesting. Before I go too deep into what pointers are, and so it's actually very rare, and you haven't seen this yet, for me to say, I'm going to spend I'm going to spend like 20 minutes just talking about the theory behind something before I even talk about the variable that we're adding here. This is one of these concepts in computer science where, so I've got friends who have been in the computing industry now for 15, 20 years. They're very experienced senior software engineers and things like that. A lot of them didn't get this concept for a good 6 to 12 months after they first saw it. So I'm just going to put that warning out there now that this is not easy, but it's pretty useful and it's kind of fundamental to how computers work. So we teach this as the idea that being able to address memory directly gives you a deeper understanding of what a computer does. However, I do fully understand that some people are going to look at this and say, that's really complicated, because we've got our variables, and now we have meta variables that refer to other variables, and that's what the pointers are. So don't worry too much if a lot of the pointers have a really weird syntax as well. So there's two things that we're learning here that are difficult. One is the abstract nature of what a pointer is. It's nearly a variable that we rarely use the value of the variable itself. All our other variables, we use their value all the time. We're passing their values around, we're outputting their values and things like that. The pointer, we're rarely using their value in and of itself, but we're using their value to get access to another variable. The pointer stores the memory address, actually. So there's that, and then when we start using these in C, you'll see the syntax of them is super fiddly. They use some random symbols instead of any kind of words or anything like that, so it's harder to understand exactly what's going on with them. But bear with me, I'm going to talk it through, I'm going to try to explain it in the easiest way we can, and then we'll get an idea of what's going on. Oh no, there are pointer puns happening in chat. I think Shrey said, no, Tom started off, I think, that your tutor can give you a few pointers about pointers, and Shrey said you'll get the point of them eventually, and Gira-chan said, as long as you point me in the right direction. Okay, I wish I hadn't read that. Okay, pointers are a new variable type. So a pointer is a variable that holds a memory address. So as opposed to something that holds a particular value that is going to be used as the number itself, they store a particular value that is the location of another variable. So when we think about pointers, we're usually going to be thinking about pointers as saying, this pointer points at this. So this pointer points at that integer over there, or this pointer points at that element of the array, or something like that. So we're going to start to think of these things not necessarily as their own variables, but as variables that specifically are there to reference other variables. So if I was talking about variables being a house, and the house contains some information, the pointer is basically another house, and the information that it stores is the address of a house. So the pointer says, I'm the address of another house somewhere. It's also its own variable, so it's stored somewhere in memory. But we don't worry too much about that. We actually think about the pointers as being an address, and then the house somewhere else as being the other variable that the pointer is aimed at. So it's kind of like, let's store a variable somewhere. So let's store a variable at UNSW. So UNSW, I actually don't think it has a number address, but it's on Anzac Parade in Kensington in New South Wales. And so that could be considered its address. So if we're thinking of human addresses like that, the pointer is a variable that says, I could give you that location, and if you have that location, you will be able to find UNSW. So in the same way that anytime you want to get somewhere, you would type into your map application. So if it's Google Maps, or if it's any other mapping application, you would type in the address to something, and it would show you how to reach where you need to be. The pointer is like that. So the pointer says, I have the address, and then if I ask the computer about this address, the computer will say, there's that piece of memory that you need. Read what's in that piece of memory, and then you'll be able to get to that variable that you're after. Someone said 2052. Yes, UNSW has a postcode. I think, yeah, UNSW is so big it has its own postcode, because it's basically an entire suburb as a university. Makes sense. There's so much mail going back and forth to UNSW. Okay. Trying to find a place to move my face there. Okay, so pointers, like any other variable, are going to be declared. They can be declared and they can be initialized and things like that. Pointers are done in a specific way, in that they have their own symbol. A pointer symbol is the star. So this is the bit where I said that things are going to get fiddly, because pointers are just done with symbols. They don't have specific words attached to them, so there's no keyword pointer in C. Instead of there being a keyword for a pointer, there's just the star. Also, I thought someone would like to say hi. She's just crawled onto my lap to say hi. So every time we declare a pointer, there's two things that we need. I gotta do my hand waving down here in front of Chicken. So the first thing is the star says this is a pointer. But the other thing is all pointers still have a type. And the interesting thing about that is every pointer has an intention that it aims at a particular type of variable. So I don't get a pointer that's just sort of a generic pointer. I get a pointer that is an integer pointer. So this declaration here says this variable that I've called IP is a pointer because it has the star, and it is aimed at an integer type, which means that if I was going to look at what's in this pointer, it would look at 32 bits worth of memory at whatever memory address that it's storing. So this is the declaration of a pointer. And if I want to do I could put a semicolon here saying, okay, that's it. But if I want to initialize the pointer immediately like this with the equal sign, I would then want to give it the address of a variable. Now, this and we have seen before. And I said that I was just going to use it and I would tell you about it later. So the and says, where is this variable? So I said my computer was going to my computer was going to take this I that I said, this human name, and sort of translate it to, the human calls this thing I, but I as the computer, too many I's, the computer is going to store that in a particular memory address, and it will see this and go, okay, I'm going to be able to translate back and forth between these. And this AND is our way of saying, as the programmer, I would like to know what that address is. Where did you put that I? So that I somewhere in memory, and this is me asking where it is. So scanf actually does that, where we say, scanf says, I will write some information into memory somewhere. And us putting that and there is actually us saying, we would like to know where this variable is stored so that scanf can write some information into it. And likewise here, I'm saying and of I, and is just saying, what is the address? So this says, please tell me the address of UNSW. And so it will write down UNSW Kensington 2052 or something like that. All right, Chicken's decided she's had enough of you. So we'll go back to just me here. So what we get then is we've created a pointer here and its name is IP. What it stores is the address of I. When we're programming, we don't know what that is, because we don't know where our program's going to store this memory. We don't know what set of addresses necessarily the computer's going to use for our variables for this. So this is going to be a number that our computer gives us that says this is where we kept your things. So all we need to know though, so we don't really want to delve into the numbers themselves, but we know that from here on, this pointer IP will give us access to this variable. So its value is 100. The pointer's value itself is whatever address this variable is stored at. It'll be a weird, complicated number. So something between, 0 and 16 billion, we decided was my my address space for my computer. But it may not even be in that address space. Your program may have its own address space, and that's the way that it would see memory. I'm definitely not going to go into details about that stuff. Again, if you want to get deeper into that stuff, there's more subjects that will go entirely into the idea of how memory is used for programs and things like that. For the moment, we're just going to learn how to do this particular thing. Girachan's asking why pointers have to be addresses. Why addresses have to be integers. That's because, as opposed to in our human world, where you could say subdivide a block of land, and you say, okay, this is house 102A, and this is 102B, and we split this thing up into half. In our computer memory, we don't actually split things up like that. So we address each 8-bit chunk of memory at a time. So each byte of memory we address with its own number, and we never subdivide those. So in a computer, we're just using integers. I could conceive of a possible future in computing where we do subdivide those into smaller amounts, and we'd say each address now has a half. So we have the address, 106 or whatever we had before, and then 106 and a half will address you into another 4-bit section of that. But the way that most of our programming languages are set up, with everything being multiples of 8s for the size of things, it's very rare that we would need that. So we would end up using these half addresses so rarely that we don't necessarily need them. So in general, what your computer will do will just always pick up these 8-bit sections one at a time and never worry about having any more fine-grained addressing. Okay, so just talking about pointer types, the type of the pointer is the type of variable that it points at. So integer I, so an integer pointer would have the integer type. A double pointer here would have the double type. So depending on what kind of variable your pointer is aimed at, it will say what type it is. And this will change when we start using the pointers to access things. This will change how much stuff the pointer accesses. So simple example is the two variable types we have so far. The integer has 32 bits of information and the double has 64 bits of information. So an integer pointer will access 32 bits. So you look at one address and it will count 32 bits along and go, okay, this is the thing that I'm accessing. The double will count 64 bits along. Sorry, just going off my camera there. It'll count 64 bits along, which is double the length of the integer, and it will look at that much information. So the addresses might be the same kind of number, but how much more memory after that first address location that is read for the pointer is different, depending on the pointer's type. James asking if the IPDP naming thing is required or is just a convention. It's not at all a convention, this. This is just me using names for things because I don't have any information. So I could use full words for these. I would always default back to your normal naming scheme for these, because pointers can be pretty confusing. So I will usually try to be really, really clear about what pointers are doing in their variable name as well. These are, in fact, I would nearly say these are bad variable names. They're just here for the example. As we go in, you'll see when I start doing examples with pointers that actually have some context, then they'll get better names. Yes, Osama has a really good question there. I still don't get the point of pointers. Can't we just access the variable itself? Yes. When we go deeper, you will see the reasons why pointers can be useful. But I do understand, because there's a lot of functionality we can create without ever needing them. So I'm going to show you some examples as we go along. And today I'll show you at least one function that you can't do without pointers. And then when we see that, you'll see how this goes. Eric is asking, do we always declare and find the address in the same line? We don't necessarily. So sometimes we make a pointer and then we wait until we've created something else and we say, okay, now this pointer aims at this. Or, for example, we could have a pointer that starts nowhere to begin with, and then it starts aiming at an element of an array and it moves through the array and stuff like that. So it's nearly like our int I, which is our index that moves along by changing its number. A pointer can change its value to aim at different objects as it goes along. Speaking of, as you said, declaring and addressing, if we don't declare an address at the same time, we have a keyword null. So null is in all capital letters, and it being in all capital letters should give you a clue as to how it's used and what it is. If it's in all capital letters, it's probably a hash-defined constant, which null actually is a hash-defined constant, and you can get it from nearly all the C standard libraries. So nearly all of them are going to hash-define null in that, and you don't have to know what null is being hash-defined to. So it's hash-defined to an integer. Pretty sure it happens to be 0, but it's not really important what the number is, but we know that we can use this as meaning that the pointer is not aiming at any particular variable. So the pointer being an integer value means any value that we could give a pointer might be a piece of memory somewhere in our computer. And so we don't really want to have these pointers just randomly aiming at memory somewhere. It might give us access to changing something that just crashes our computer, or we'll change code in our program so it doesn't run anymore. Something like that could go weird. So when we say that a pointer is not aimed at anything yet, we will say it's null. And we can initialize pointers to null if we know that we don't have a particular variable for them to point at yet. Okay, I'm not covering up any text with my face there. So at this point, we have a pointer and we have the ability to aim that pointer at another variable, but I haven't told you yet how we actually get the value of that variable. So what we need to do is, if we have this situation here where I've created a pointer that points at I, for me to actually access what I is using the pointer, I actually use the star again. So this is the confusing bit about variables, and it's very similar to arrays, where the square brackets for the array, when we were creating the array, was going to give the array a certain size. When we're creating a pointer, the star says this is a pointer, and it doesn't necessarily have any information in it yet. But if we initialize it, or at any point we set its value to the address of a variable, then we say that that pointer is now aimed at that variable. So this pointer is aimed at the variable I. in order for us to then say, okay, what is the value at the end of the pointer? We use the star again. So the star, I like to call the star at this point, is our Google Maps. So this star says, put this address into Google Maps, find out what's at the other end, and then read the information that's there. So this here will read the value of the variable I. So it will take the pointer, follow the pointer to its address, which is this variable, read 32 bits of that variable, which will give us the number 100, and then we can access the number 100 there. So to get the variable, to get the value of the variable that the pointer is aimed at, we use the star again. So this is where I think that a lot of the confusion comes in with pointers, is that you've got this symbol that does two different things, depending on whether it's declaring a variable or whether it's being used on a variable that already exists. So the star says, I'm going to go to something and find out its value. If I don't use the star and I'm looking at the value, then I'm going to get the value of the pointer. In fact, I should probably jump in here. I actually have some demo code on pointers that I have available on the class website in the lectures section. I'm going to quickly make a directory for lecture 8. And I'll grab it the same way that you can get it there. So lecture section, what week are we in? Week 4. Pointers demo. Download that. Shrey's sending me a message there. I'll read that later. Okay, so I've downloaded that. Oh, not that terminal, this one. Did I download it into lecture 8? I think I did, yeah, pointers.c. So we'll gedit this, and we say, this section here is the section in the slide that I've got. So create a pointer, and it stores the address of I. So I'm just going to comment out this other code here, and just show you this section here. So I'll save this, compile it. So dcc pointers.c, and I'm going to call it pointers demo. And I'm going to run this now, and then you'll get an idea of what that code is doing. So this is saying, so %p is something I haven't shown you before. This is the way that we can look at the address of a pointer if we want to. So it formats the pointer variable in a different way than %d would format a normal integer. So we get this. So this is the number, which is the address of that pointer. This is a really weird number because it's got a lot of letters in it. This 0x at the beginning signifies that this is a numbering format that we call hexadecimal. Hexadecimal means that this thing has 16 possible digits, 16 possible values for each digit. So it goes the numbers 0 through to 9, then A, B, C, D, E, F. So this is actually a valid digit, this is a valid digit, this is a valid digit. It's just a different way of looking at numbers. So you know how base 10 had 10 possible digits, binary, which is what we've been using a lot, base 2 has 2 possible digits, the 0 or the 1. This has 16, so I don't have enough fingers to hold that up, so 10 and 6 possible digits. It's just used that way because 16 fits better into something that fits in binary memory than the base 10 system that we use. But this is how our addresses are stored. They're stored in this kind of way. So somewhere in my computer, actually not my computer, this is VLab, so this is on CSE's computers, there's this memory location, and that is where the variable I is. So that's the value that's stored in the pointer itself. And then if we follow the pointer to the location that is in that piece of memory, which is the variable I somewhere in our program, and we say, okay, what can we read in 32 bits from that memory location? It reads the value 100, which we stored there. So this is the address of the variable, and then this is the value that was stored there. So that's the start of how we're getting into using pointers like that. And I've got more demo in there for that as well. Okay, so lots of conversation happening there. I'm going to move on because I see that Tom and Shrey are answering a lot of stuff there. Okay, so what we've got so far: how to create a pointer, how to aim a pointer at a variable, and then how to access the variable that the pointer is aimed at. So we've got a lot of capability there, which is kind of most everything that we're going to be using these pointers for. So now we get to the interesting thing. Pointers allow us to not create copies of variables, but pointers allow us to actually access a variable that exists somewhere else. So somewhere else in my code, I have a variable, and I could pass a pointer to that variable into a function. So if we think about the details of what's happening in a function, I've said to you before that anytime that we pass a variable into a function, it makes a new copy of that variable inside its own curly brackets, inside its own scope. And that variable can't affect the variable that's in our main program. That's what we call passing in by value. The interesting thing is now, if I give you a copy of an address of something, so we could all write down the address of UNSW. So we could all write down UNSW, Kensington, 2052, New South Wales, Australia. And we're all in different parts of the world. At the moment, we can all write down copies of that address. That would give all of us, I mean, technically, it's kind of hard right now with travel restrictions and things like that, but technically that gives us all access to the same UNSW. We are not making copies of UNSW. I mean, it's nigh on impossible to do, but it means that all of us know where the one UNSW exists, and we can all technically get there eventually. I mean, the physical limitations of this are huge, but if we were thinking about this like, you know, it's all on one computer and we could all access it, that means we're all different entities around there, but we all know where this one location is, and we can all get to this one location, which means there becomes only one. So there's no copies of UNSW anywhere, there's only one, and we can all get there. I feel like that metaphor would have worked much better when we were actually doing this course in person, but I'd never used it. Anyway, so we can all access UNSW, and it's the same one, which means that I can give the address of a variable to a function, and it can come back and change the variable that's in the main function, for example. Let's have a look at exactly how these functions work. So when I was saying before, if I had a variable in my main and I create a function and I pass in that variable into the function would get a copy of the variable. So it gets a copy of the variable, but any changes it makes to this variable do not change this variable. It's just a copy. So any changes I make to the variable there change this copy, and then nothing happens. Now the interesting thing is, if I have a variable and I have a pointer that's aimed at that variable, I pass the pointer to a function. So instead of passing the variable into the function, I pass a pointer to the variable into this function. This copy of the pointer here is aimed at that variable, because both of these store the address of this variable. So the address is going to be something like this. And we don't worry too much about what that actual number is. We just think that these are aimed at this particular variable. So if both of these are aimed at this variable and we access what's at the other end of the pointer using the star, here we will get access to this variable. So now we have the capability for this function to any changes that it wants to make to a variable, if it accesses the thing that's the other end of the pointer, it now has access to the variable that's in our main. So it now can change values that are outside of the function itself. So this is the point where, you know how I said like everything in the curly brackets is like its own little thing? The pointers are the first time that allows us to jump that rule. So it allows us to say, I no longer have to act within my little box as a function. Now, this is the first step of us being able to say, I can access something outside of my box because the pointers have given me the power to now aim at variables that are anywhere in my memory, not limited to this one piece of memory that we have here. Osama's like, it's like goto, but for variables in different functions. That's scary. I don't want anything to be like goto, but actually it is a little bit like that. You can jump outside of the standard flow like that. Shrey's very scared of what you're saying there, Osama. Okay. So let's look at two different functions and how they kind of work like this. So I have one function that says increment this integer. So I've got two functions that are there to increment integers. So that's just like just doing a plus plus. So again, trivial function. This has no real use for us, but it's an easy enough example that you can kind of see what's going on. So if I say increment int and I pass in an integer n, whatever integer I gave to this is unaffected by this function. But I create a new integer n in my function here, and I would add 1 to it. Then I would finish the function, and this function would return to where we were in the main, and nothing changed in the main because this didn't have access to anything in the main to change it. However, if instead of passing in the value of an integer, I pass in the value of the pointer, which is the address of an integer, which gives me access to another integer somewhere else. And I say, go to that integer and set that to whatever value you read from that integer plus 1. So this is going to the other piece of memory and saying, okay, I'm going to read your number, I'm going to add 1 to it, and I'm going to store that in your number, which is the same thing that we were doing with incrementing, but now this function has the capability of doing that from outside the scope that the variable exists in. So now we have the ability to say we can make changes to variables that exist in other parts of the program, so long as we know where that variable is, so long as we know the memory address of where something is. This leads us to Gautam's asking what goto is. I should probably not have mentioned goto at all. It's a really, really old programming thing that allows you to jump to any other line in your code. So you can say, at this point, stop executing where you are and go somewhere else. And it's really, really messy. It's really old school. That's like, there was goto when I started learning programming in the 1980s in a programming language called BASIC. BASIC has faded nearly out of existence entirely now. It's been superseded by much safer programming languages. Zeal's asking, if I use the global variable, it can do the same thing. Kind of, but not exactly. So the global variables are accessible from anywhere in our code. The pointers give you access to a specific thing at a time. So it's nearly like if we use pointers, we can track what we're doing more easily because we can see where things are going between our functions. Global variables are just kind of confusing. And also very dangerous because they reserve a name through the entire program, whereas when we're doing this thing with pointers, we're still maintaining this kind of control here that you only have a copy of a pointer. You can't change this pointer. So what we can do is we can say, this pointer is always aimed at this variable. We give it to this function. It can do anything it wants with that pointer in there, but it won't kind of corrupt this pointer that exists in our main. If we have a global variable, which is a variable that sits outside the scope of any particular piece of our code, it means anything can change it and we're not really sure what's going on. At least here we know we only gave this function access to this variable explicitly by giving it that pointer. So there's a subtle difference that makes this safer than using things like variables that are not inside any of our functions, which is expressly against our style guide to do things like that because they are so dangerous. Sarvesh was saying, so the address of the same number has moved up by 1. Here, we are not changing the address because we're using the star. So if I have a pointer, so the pointer is called n, and I put the star on the pointer. So the star is not part of the variable name. By the way, the variable name is n. The star is part of the... It's like the square brackets on the array. So it's a symbol that says I'm going to do something pointerly with this. So the star here says I'm not accessing the pointer. I'm following the pointer to a variable. I'm accessing that variable. So this changes the variable, but it doesn't make any changes to the pointer itself. Will's asking, can we use functions with pointers in the assignment? Yes, you can. This is something I was saying yesterday in the assignment live stream. The assignment is not designed with pointers in mind, and our solutions that we've written for the assignment don't use pointers. So you don't need them. But if you want to, you could. I would personally keep the assignment to just arrays and functions and things like that, and practice pointers in the tutes and labs coming up. You will have plenty of time to work with pointers in the tutes and labs, and really in the entire second half of the course, as well as the second assignment, which has heaps of pointers in it. Sarvesh, so you're accessing another variable, basically. Yes, and the key is we're accessing another variable that we can get access to via the pointer. So Mihir is asking, is the pointer now pointing to an n+1 value? So we didn't change where the pointer was aiming here. Let me just jump into my code. There's a big difference between... Did we actually have it here? Yes, we have the functions here. There's a big difference between this. There's a big difference between these two lines. I'm just moving this so that you can see it. This says access the variable at the other end of that pointer, change the variable at the other end of that pointer to that's value +1. This is saying the pointer itself, add 1 to the pointer itself. This would change the address of the pointer, and that would mean it would be aiming somewhere else. This is like super dangerous, because if I do this, I'm now aiming the pointer at a different piece of memory than I originally intended, and so I won't really know what's in that memory unless I'm really sure. Sometimes we can do things like move through arrays with stuff like this, but it's still a slightly dangerous move. But accessing the star says I'm looking at the value of the variable that is at the end of the pointer. So I say, read the value from the variable at the end of the pointer, add 1 to it, and store it in that variable. And this is very different. This is saying I'm going to change where the pointer aims at. So changing the value of a pointer will change where it's aiming, but using the star in the pointer follows the pointer to, you go to the house, and then you change what's inside that house. So there's a slightly different thing going on here. This is actually kind of really dangerous. So we're going to be careful with doing stuff like that for the beginning. So Max is asking, will that change the value of n in the main function if we use pointers? N doesn't exist in the main function, but there is a pointer in the main function that got passed to this. Here, it's in this code. So increment pointer IP, so it gets the pointer IP that comes in here, and n is a copy of IP. IP is pointing at the variable I, so this would add 1 to I when it runs here. So if I run this, we'll see, I'll compile this and run it, and then you'll see how that works. Oh, did I not save that? I didn't save it. Okay, compile this and run it, and you'll see I is 100, hasn't changed. So when I tried to increment I passed a variable in, and you can't make changes to a variable. So this added 1 to n, and n is not I, n is a copy of I. And then I passed in a pointer IP, and n is a copy of IP here, this pointer. And note that these are completely different n's, obviously, because they're in different functions. So this pointer here then gave me access to, IP gave us access to the variable I, and this function was able to change the value of variable I. So it added 1 to it, and variable I then changed after I ran that function. Trent, as you're saying there, so after a pointer has been declared, *n indicates the value of the variable pointed to, and n indicates the value of the memory being pointed at. Well, I would say you're very correct in the start of that. The *n indicates the value of the variable being pointed to. Yes, the *n definitely gives you access to the variable. N on its own would change the address being stored in the pointer, which I think is actually what you're saying there. So yeah, it is basically that. Yes, Girachan's got it got a really good nuance on that. N is an address. *n, is not part of n. Is a separate command. So you could nearly consider to be a function that runs on n that says follow this address to its location and get the value that is at that location. So get access to the variable that's at that location. Paco's got it as well. *n is like a transport to take you somewhere. Yeah, that's why I called the Google Maps. It's the action of actually going somewhere to do something, rather than n being the address, or not that n, this n being the address you want to go to, and putting the star in front of it says I want to actually travel there. I don't want to just I don't want to just know that UNSW exists. The star says I'm literally going to get on the train, go to Central, and get on the bus or the light rail to get to UNSW. Okay. So, there's a lot of good discussion going on there, which I think is really good, because this is a concept, as I said at the beginning, this is a concept that's hard to grasp, and it takes some time to get into. One interesting thing that we can do now is, previously in functions, the most number of variables that we could think of changing, and wasn't even changing with a function, was we could output one variable. So if I had a function where I wanted to swap the values of two variables, that was completely impossible until pointers. But now we have pointers, I can say, I'll give you access to two variables. Now please swap their values. And this is actually pretty simple. So I make a temporary variable, copy one of the values into the temporary variable, write one over the other, and then copy the temporary variable back into the other one. So this is a really, really simple function that all it does is it takes the value of two variables, moves one to the temporary, copies the other one over, and then copies from the temporary into the other one. So it ends up being that these two swap after a little bit of juggling around like that. This function was completely impossible before we got to this point. So without the pointers, there's no way that a function was able to access two variables at once. Another thing that's interesting, and this is a question that had been coming up, yeah, Tom's the two Toms are talking about buffer overflow, which is something like, so pointers can give you access to nearly anywhere in memory, and arrays give you access to a chunk of memory. There used to be a way that we'd read off the end of arrays and go into other space in our program, and somewhere in that memory is the running code of our program, which we can then edit. And then you could do this for what we call like code insertion hacking, where you can get code and put it into someone else's code by using pointers to overwrite other parts of their memory and stuff. We're not going to go too deep into that. But I want to talk about arrays, because arrays are really interesting. Arrays are blocks of memory. So arrays are a mini version of this kind of infrastructure I'm talking about. A memory exists, it has addresses, and we have pointers, which are numbers that access those things. Arrays are just like that. They're blocks of memory, and they have indexes, which are numbers that we use to access individual elements. The other thing that's really interesting about arrays is the name of the array. So if I take the square brackets off this thing, and I say the name of the array, it will actually print out the address that the array starts at. So when I'm just passing around the name of the array, I'm not looking at an individual element, so there's no square brackets here, just looking at the array itself. And I print out I print that out as a pointer. That's actually going to be the memory location of the array, which is why we had some questions before. People were asking me, how come when I access an array in something like a function, I can change the array? And the reason for that is the array variable. If I don't use any square brackets to go to an individual element in an array, the array variable itself is the memory address of the array, which is exactly the same as a pointer to the start of the array, which means that if I pass an array into a function, I can then change the array itself. That's going to probably come in a bit handy in the assignment. You'll see that in the assignment starter code that there's a function there that takes in the canvas and wipes the canvas clean. It sets it all to zeros. And from what we knew of functions, you would have looked at that and said, how could that be affecting the something that's in our main? Because it's passing something into a function. It should have been a copy. But the copy of the array is actually the copy of the address of the array. So the array still only exists once, and then we get access to it in memory. Okay. Pointers are variables. This is this funny thing that I'm going to say about nearly everything we do in programming. Is like, while loops are code. While loops can contain while loops. Pointers are variables, which means pointers can point at pointers. Now, if your head hadn't already exploded from just grasping what pointers are and how they work, at this point is where it just goes... I'm going to say that we are not going to use pointers to pointers at the moment. You're definitely going to use them in the future. There are needs for them. If you continue working in languages like C and C++, I mean, C and C++ are kind of, they're kind of twins in that they can both run each other's code to a certain extent. But there are uses for pointers pointing at other pointers, but at the moment, in this course, we're not looking at that because it's very, very difficult to get a handle on. But I'm just going to let you know they exist, but just be careful with them. Also, just wanted to put this meme in here anyway. Okay, so we're going to go on break. And I just wanted to say something a little bit about assignment 1 here in the break. Assignment 1 is CS Paint, which is an analog. It's our kind of version. It's our very, very simplified version of the venerable Microsoft Paint program, which is like more than 20 years old now. I mean, it's been updated over time, but not by much. It still has the kind of same simple ideas in it. But I think that we were talking at the beginning of the lecture today about what follows from coloring pixels. From coloring pixels on a canvas, we can get the idea that everything on our computer, the canvas, if it was just stretched to fill the entire screen, everything that we do, all the complex 3D graphics and everything like that, is just taking a 2D array of pixels and changing what color they are. So if all we do is we look at every pixel on our screen and we set it to a particular color, that is everything that we do with visuals with computers. So we're talking 3D games, we're talking even VR, because VR is just two screens in front of your eyes. It's not really that different. All your blockbuster movies that have CG in them and all that kind of stuff is people just saying, what's every pixel on the screen and what color is every pixel on the screen? That's it. At the most fundamental level, that is the only thing that all our computer graphics is doing. So what you're doing with CS Paint is technically possible if you write enough code to do a lot of different things. It's technically able to set up the same kind of thing to do a full game, you know, or render an entire action scene from a big Marvel blockbuster or something like that, where it's more CG than filmed, you know. So that's where it all comes along. So there's here is the reference solution where you can play around with CS Paint and how it works if you want. Okay, so we've gone pretty far over time, but I think it's kind of necessary for pointers. And don't worry, the example I'm doing today is shorter than a normal example, so hopefully we'll still squeeze all of it into the second hour. So we're at 12:19 now. I'm going to take a shorter break than usual. I'm going to only take, like, say, a 3-minute break, and we'll come back at 12:22 and continue the lecture. Alrighty, I'm back. Alright. So, let us create a program that is using functions and pointers. I don't have like an amazing theme for this one. It's just something that I made up that's going to use that swap function that I showed before. It's called a jumbler, and what we're going to do with this program is we're going to take some numbers. We're going to kind of fiddle around with the order of those numbers. I don't want to say the word randomize because that has like particular connotations of doing things, but it's gonna shuffle them a little. There you go. When I say shuffle, I don't mean I'm not capable of fully randomizing this at the moment, but it's going to change the order of some of the numbers and then print them back out. So this is a pretty simple program, but what we're going to see in this program is the ability to use things like functions with our arrays, passing the arrays into functions, using pointers to get access to things and to move them around and stuff like that. Hopefully this will show you a little bit about how these pointers work in the wild, and also a little bit about, to continue on from our beginning work on functions, is to show you how you can actually do some really interesting structure with functions to make a program look really nice. So, first thing that I always do when I'm thinking about a program that I'm going to write is what are the little pieces that I'm going to write to make up this program, and I split it up so that I don't have to do it all at once. What we end up doing when we split up a program into its parts is we actually split it up into its different functions. So its different functionality actually lead to why a function is called that name, why it has the name function. If we break something down into its little pieces of what it can do, and then we build those together into its main function, so its main capability, you can see I'm starting to use the C keywords as the English words that they are, which is where we're getting into the philosophy of how we actually do programming, which is what the people who wrote these keywords in the first place actually meant when they're talking about it. Oh, someone's back. Yeah, so I'm going to have a function that reads input. So that function's going to do, say, multiple scanfs and put them into an array. We know this. We've seen this. I could nearly grab code that I had the scanf demo for previously and copy paste it in here. I want a function that swaps two numbers. I'm going to take the one from the lecture slides. But then I want a function that doesn't just swap two numbers once, but it goes through the array and swaps lots of pairs of numbers to shuffle or jumble the array. And then I've got a function that prints that back out. Actually, now that I think about this, I should actually change this demo to talk about shuffling a deck of cards, because it's not that much different from that. Okay, so I don't necessarily need to go into the slides too much here, but I'll keep them around as a reference, and I will come in to my VLab here and start creating this. So I'm going to gedit and I'm going to call it Jumbler. Actually, you know what? I'm going to call it Shuffle, which is actually different from the name that it's supposed to be, but me thinking about like using this as a more kind of as an example that we could think of in the real world. So take in hang on, I should say Shuffle can read in a set of, let's just say, a small deck of cards. It will partially shuffle that deck, then print out the new ordering of those cards made by me. Email address to get in contact with me if necessary, and we are still in October. I mean, like, you know, 2020's gone for at least 10 years now anyway, right? Okay, I think that I'm only going to need standard input output, but I'm not sure. If I think I'm going to need other libraries later, I can add them in. And there's my main. Okay, so there's my starting point. So first thing that I want to do is I would like a function that read the input and store it in the array. So I would like a function that, for example, is able to work with different decks of cards. So I'm going to define a maximum deck size. Let's say 52, but that's just the standard, you know, set of playing cards. But we may not actually be using all of those. In the examples we're going to do in the code as I run it, we're definitely not going to use 52 because I'm not typing in 52 separate numbers every time we want to test this thing. So I would like a function that is going to shuffle a deck of cards that already exists. So I think that the way I'm going to do this is it's actually going to be a void function. Oh, sorry, it's not going to shuffle. This is the first function here, which is to read the input and store it in the array. So I'm going to call this one read input because that's a good name for it. So this is reading input from the user and storing it in an array. I don't think I need to give any information back, but I'm not sure. Did I give information back? I did. So maybe we can give back the count of how many inputs we actually read. And this is a convention I'm using because scanf does that as well. So like maybe this is useful for people to know that when they run my read input function, that they know exactly how many cards went in. Because maybe someone tells me, I want you to shuffle 60 cards, and I'm going to say I will only read in 52 of those. So maybe this will end up 52. Returns the exact number of cards read in. Our cards at the moment are just going to be integers. Okay, so if I'm going to shuffle this deck, I need to know where the deck is. Sorry, not shuffle. If I'm going to read input and write it into the deck, I need to know where the deck is. So I'm going to say there's going to be a deck of cards, and the deck's going to be maximum deck size. So take this function, put it here, and then start to write it. So if I want to read in an unknown number of cards, I might actually want to ask the user how many cards there are. Then I'm going to loop through and scan in the cards, write each number scanned into the array. I like to do this to be a bit like, okay, this is the steps that I think that this function needs to take, and then I will write the function. I do have other functions that I'm going to want to write, but I'll look at them in a second because I've got these 4 functions, right? One of them reads the input, another one swaps 2 numbers, and that should be easy, so I should have swap. And then one of them swaps several numbers, and one that prints out the numbers. So what I will probably do is pick the order that I'm going to do these. So what I'll do is I'll read in the numbers and print out the numbers first, because that way I've got my testing thing set up. So, I don't think that one even needs, like, if I'm going to print them out, print deck. This is also going to take the deck. So a lot of these things are just going to take the deck as the input and then do something with it. Okay, so print the deck is going to do that. I won't work on 2 functions at a time. I'll finish this read input one, and then I'll write print deck, and then we'll be able to test whether it's working or not. Okay, so first thing is ask the user how many inputs there are. How many cards are you entering? And if we're going to ask them to type something in, we're expecting something to come in. I'm not going to, for the sake of this example, I'm not going to do too much validity checking on the scanf. So I'm not going to, if you want to, you can go back to our old dice checker example and say, if we did want to check the validity that this was between 1 and 52, you have code to do that already. I'm not going to bother for that today because there's other things that I want to do with the functions and stuff. So we're going to scanf a number, and that number has to go somewhere. So I'm going to need number of cards. Let's go for the old -1, so that if the scanf didn't work, at least I would see the -1 turn up somewhere else, and I know there's a problem. However, the scanf will replace that -1 with the actual number if this works properly. Okay, so this will tell us how many cards we're entering, and then we're going to loop through and scan the cards. So if I'm going to loop, I'm going to start with a standard while loop. I just add some white space when I'm doing things so that's closer to the middle of your screen. It's easier for you to see. So I'm going to do a standard while loop here that's going to go through up until the number of cards. So this is our bog standard while loop where we know we have a number of times we're going to do something. We'll start with 0 and we'll end at when we hit that number, but we'll only run every time we're below that number, which will give us the exactly right number of things from 0 to that. Will also give us exactly the right indexes to put something into an array. So while I is less than num cards, we will scanf and put it into a particular point in the array. Can anyone see? Happy for people to tell me now in chat. Can you see where this breaks? Someone can just basically yell out in chat if you can see how this particular while loop here, the way I've written it, will break my program. So I'm going to put this into the deck in the location I. Has anyone noticed yet? I'll give it to you because I want to go quickly in this example. If I say how many cards we're entering, oh yeah, there we go. Trent's picked it up. Jamie has a potential issue there. Girichan has the same kind of thing. Alex, I don't think it's an infinite loop because my I++, I have remembered my I++ this time. So I wrote the I++ before I wrote the rest of the loop this time. So I can't keep pretending that that mistake is intentional and that I'm just trying to trick you. Okay, so this is fine. The I++ is working. However, here, if the user gives me a number larger than my maximum deck size, this thing's going to go off the end of the deck and it's going to try to write something into memory that it doesn't have access to in the deck. So I do want to make sure that that's not the only thing that's happening there. If I is less than num cards and I is also less than the max deck size, then we're okay. We can do that. The other thing also is this thing is definitely going to blow up, as someone said. If someone gives me a negative number, or this remains -1 and doesn't, if the num cards here doesn't replace the -1, which means if the scanf here doesn't work properly and this remains -1, actually no, I think we're okay there, because if this remains negative, this while loop never runs. So we're never going to try to write to a negative index, but the issue was that we could go over max deck size and then try to write outside the array. So I've added a second condition in the while loop here. So either I go up to the number of cards you've told me, or I go up to the number of cards that I can fit, and I won't go over either of those. This comment is actually in here. Right. So what I've done there is I've looped through and I've read all the input that the user has given me, and I've said this is how many cards I've written in. I'm supposed to return the exact number of cards that I read in. Have read I cards, and that tells me how many cards I've read so far, but also at the end of the while loop, that condition is also correct. So when I get to the end of the while loop, I have read exactly I number of cards in, which means I can return I to say that is the exact number of cards that I read in. So every time that I run this, it will tell me how many cards I read in by saying this is exactly the number of times that we ran scanf. So this is why having this iterator here in the while loop gives us a lot of information. So I've just added these comments here so we kind of know exactly where we are. When I'm reading my while loop, I know every time I enter the while loop, I've read I cards previously. And when I exit the while loop for the final time, I ends up being the number of times that I read cards in. So whether or not it hits the number of cards the person said, or gets limited by the maximum deck size, I is definitely exactly the number of times we read in stuff. So it's nice to have that variable that counts what we're doing while we're in the while loop, and that's the thing that I can return. So read input then says this is the size of the deck that we're working with. So what I can do now is I can say int deck size is equal to read input. Oh, read input needs an array to write its input into. So I need to make an array, which is my deck. That's going to be max deck size. I'm going to set it to zeros for the moment. I guess that's okay. I'm going to assume that there's no cards that are a value 0 for the moment, but I don't know that for certain. Maybe there are certain decks that have a 0 in it. But for the moment, I'm going to say, okay, zeros mean no card, and any other number is the card. I don't know, because I don't know exactly what game I'm looking at here, but if I was looking at a normal deck of cards, they go from ace through to king, and so none of them are a 0, so maybe I'm okay here with this. It's like a potential risk for the future, but I'm going to leave it like this because for the purposes of the example, this should be okay. Let's go print deck now so that we have some output. If we don't have the output, it's really hard to know whether things are working. Okay, print out the cards in the deck. I'm going to change this now because I'm thinking about this. I don't want to print out the whole deck. Because what if the deck I'm shuffling is a small deck and it only has 10 cards in it, and I just print out the whole deck, 52 cards. I'm going to print out all these zeros. It's not actually what I want. So what I would also like is an integer saying current deck size. So this is the amount of this deck I'm using. So, you know how when I was first talking about arrays and people were saying, what if the array is not the right size for what you're using? So what if I'm not sure how many things I'm going to use, and so I know the maximum is 52, but a lot of the time we're only going to use parts of that deck? This is me setting up that structure. So I'm saying this is the real deck size, and that can change depending on what my user has told me. And so what I'm going to do now is that every time I'm going to use this, I may have a deck that is capable of storing more than I need, but I'm only going to use part of it at a time. So I'm going to go from the beginning and I'm going to use that many items. So if my user gives me 10 cards, then I'm going to say the current deck size is 10, and I'm storing that here in deck size. And so if I'm going to print it back out, I'll say I know that I'm only using the first current deck size number of elements of that. So let's just actually make sure read input is working correctly. Read input required the deck. And now I have the deck and the deck size, which means I can do my print deck and say we get the deck of cards and we say the size of the deck, the number of cards in the deck, goes into print deck so it knows how many it's going to print out. So in order to print out elements of the array, this is something that we have seen before, is we're going to loop through the array. So I'll make my while loop. I is less than current deck size I plus plus. And for each element in the deck, I am going to do a printf. Oops, printf. And I'm gonna do their number and then a space. And the number that I'm printing out is I. So the index moves through the deck and then prints out each of those numbers as it goes along. Yep, I'm just looking back through a lot of what people are saying. Oh, Trent's saying like if this was an Uno deck that has zeros, right? Uno has zeros. So maybe the 0 is a bad thing to have there, so we've got to be careful. And Raymond saying, would current deck size be the I returned from read input? Yes, it would. So we store the I from the read input in the deck size, and then we pass that into the print deck. So this says, okay, I'm limited to using this much of the deck, and I might, just to be nice, print out a new line at the end. So the deck is going to just print out the numbers one at a time, and then a new line at the end. And it's a void function, so I don't need to return anything, it just finishes. And I don't think there's anything else I need there. So let's compile and run this and see how it looks. DCC, what are we calling it? shuffle.c. My output file, I'm just going to call shuffle. All right. So let's run shuffle. Shuffle says, how many cards are we entering? I'm going to take this easy for the moment and just say, okay, there's only 4 cards that I'm entering. I probably should have put another line there saying, okay, enter cards now, but anyway, 6, 7, 8, 9. Note that if scanf is doing multiple things, you can have enters between things or spaces between things, but so long as it gets the right symbols, it should be able to do stuff. Alright, so it read the cards 6, 7, 8, 9 into an array that actually had space for 52, but we're not using all of it, and then when we printed back out, it printed out the exact number of cards that we had. So I'm pretty sure that my first 2 functions are working. My ability to read in and limit the number of cards we're using from this deck, and then print it back out. So I've actually done the first one and the last one. Now let's look at the function that swaps 2 numbers and a function that swaps several numbers. So let's have a function that swaps 2 numbers. This function is going to take the memory addresses of 2 individual integers and swap the values between them. I'm going to come back here and say this is exactly the function I'm going to use, because I wanted to show a function that has to use pointers. So we've got 2 integer pointers, and we're going to say the values in those integer pointers are going to get swapped over. So integer pointer card 1, integer pointer card 2. Swaps the values stored in integers that card 1 and card 2 point at. Okay, so I should actually just kind of show how that function is working. So what it does is it has a temporary integer, and that temporary integer stores whatever value was in one of these 2 cards. So it's kind of like we've got this situation. So here's my main. On my main stores somewhere the number 6 and the number 8, somewhere in its memory. When I call the other function here, so this is my main memory, and this is my swap memory. So the main has 1 pointer here, points at this one, and 1 pointer here that points at this one. The swap gets a copy of those pointers. So it's got 1 pointer here, and another pointer here. The swap then, that's an integer variable, that's an integer variable, creates a new integer variable here called temp. And let's say this is the first card. So it copies the first card 6 into its temp. And then it says, look at your other pointer and take that value and write it over this value. So if we're writing it over it, this one gets wiped away. And it becomes 8. And then we take the value from the temp, which is here 6, and we write it over this one. So this one becomes 6. And then what we've done then is we've swapped those 2 values using this little bit of memory here to store one in between while we're changing things around. So that's what our swap is going to do. It's going to take those little steps there. So store one of the values in the temporary by saying, what's the value of card 1? And then we say, because we saved the value of card 1, we can now override it. So we go to card 1 and we say, you're now equal to whatever was in card 2. Ooh, that was going to break something. Did I do that up here as well? Yes. Was someone trying to tell me that? Yeah. Everyone's like, it's behind you. Zeal thinks it's on purpose. No, I just make typos sometimes. And Sean's like, he's going to ask us why this won't work in a second. And I love that everyone thinks I'm so smart that I don't make mistakes, and then everything is a trap. This is the secret for being a teacher, is like you pretend that every mistake you made was a test for your students, when it wasn't. It was just purely a typo that time. I think it's good to also know that like human error sneaks in everywhere, and it's not really about whether or not we make mistakes. It's about figuring out how to catch them and figuring out how to solve them if they do come up, because that kind of typo is going to appear in lots of people's code and in lots of different places. Okay, see, I have the benefit of having 99 people watching me while I code. So it's just like, it's really hard to make a mistake, because every little thing that I do wrong is going to get caught by people, and I get a lot of help. I think every programmer could do with this kind of benefit. Anyway, so card 1 then gets the value that was in card 2. Because we saved the value of card 1 here, we don't need it to be stored in that variable anymore, so we replace it. And then, so card 2's value is in card 1, which means card 2 can now be overwritten with the value from card 1, and we'd saved that there in the temp. So card 2, value of the variable, we're not changing any of these pointers, then becomes the variable that we stored in temp. So it's pretty simple. Am I missing a step? Oh no, I just put these, I knew there were 4 lines in that, but I was sure I was correct. I just put these 2 together, which is fine. Okay, so this swaps the value of two integers. So we can test whether this is working by throwing it in here. So if I want to swap and I need 2 pointers, remember that a pointer is the address of a variable, and I can use the AND to get the address of a variable. So I could say AND deck, and I'm just going to go out on a limb and hope that these things have actually been created, but I can say, what is the address of the variable deck 0? This is going to give us the address of the first element of the deck, and then I'm going to say the address of the second element of the deck here. So really, really interesting. Swap says I need an integer pointer as my input, and I have said an integer pointer is a variable that stores the address of another variable. So if I want to, I don't have to create a pointer to put in here. I can just give you the address of the variable. Isaac's asking, can I point to multiple variables with one pointer? Not at once, but you can point at a variable with a pointer and then change the value of the pointer to the address of another variable and say, okay, I started off pointing at this and then I pointed at that. But you can't point at more than one thing at a time. However, if you point at an array, you're technically getting access to more than one thing at a time. So it kind of works. Okay, so swap deck 0 and 1 should swap the first 2 elements of my deck. Let's test that working. So you can see how every time I write a function, I want to at least run it once to test. If I had more time, I would definitely be testing these in multiple different cases before saying, oh yeah, this works, you know. Okay, so we run shuffle and we say how many cards are we entering. So let's enter 5 cards, 1, 2, 3, and check out how scanf is able to ignore a lot of the differences in what I do. It's going to run scanf 5 times. It's ignoring the enter that I pressed there, but it's still going to read these 5 numbers in. So those are the numbers I wrote in, and then after I've written those numbers in, swap has swapped the first 2 of those, and then print deck prints them all out, and so I've got 2, 1, 3, 4, 5. So at this point I can see that the swap function is probably working because it was able to swap the first 2 numbers. Now, the important bit of what we're doing is the shuffle. So the shuffle is something that's going to work on the deck, so I'm going to need both the array, the deck itself, and also how many of those elements we're going to use. I should copy paste that. So there's my shuffle function here. Shuffle will call the swap function multiple times on the deck. It doesn't have to return anything because it's just making changes to this deck, and that deck will then exist up there. I'm going to take out this swap code because I don't need that anymore. Okay, so if I want to call this multiple times, I'm just going to make up a way to call this multiple times because I'm not using any kind of random number generators to decide indexes or stuff like that yet. I will show you random number generators later, but I don't think they're necessary now, and they will like kind of cloud the message of what I'm doing. So grab 2 cards and swap them I'm going to say do this multiple times. These aren't great comments for me to code on because they're kind of in a weird order, but that's okay. I'm just going to remember what I was going to do. So this, by the way, is a very bad comment. Just don't leave. You know, when you're writing comments to plan what you're doing, some of them should not be left in the code. So this one's definitely bad in terms of something that's going to explain the code. So I'm going to do a while loop that's going to go through all the cards in the deck. So up until current deck size, it's going to go through every card in the deck, and then it's going to swap one card with another card. So I'm going to say other card, and I'm just going to make up some way of finding another card. So other card is equal to I times 2. So it's going to be like, you swap the first one with itself, no big deal. You swap the second one with the third one, so you swap 1 with 2. Looks like my Slack pop-ups are turning up on my screen. Sorry about that. I might just quit out of Slack so that we don't accidentally get confidential information turning up like that. All right, so this is going to, so 1 will swap with 2, 2 will swap with 4, etc. But we're going to get a point where, yeah, Tom's there right now. We're going to get a point, well, I should have turned off Slack before starting the lecture, or at least turn off the notifications. And then we're going to get a point where this doubling is going to mean we're going to go off the end of the array. So what I might do to keep this in the array is going to mod this with deck size. So the mod of deck size means that if I get a number too big for the deck size, it will turn into its remainder. Give a chance, like, open your email as well. You want me to open the Google Drive, which has all of the theory on what we're going to put in the exam and stuff like that as well. Anyway, so this thing here could be anything, right? I'm just making up something, so this is not code that's not super important. Other card is just a made up way of grabbing another random card. It's not actually random. That's why I put it in quotes. So if I have one card and another card, then I can call the swap function on that. So swap the address of I. So that's one card in the deck, so that's us just going through the deck. And then the address of the other card in the deck that we're looking at. So what this is going to do is it's going to go through the deck and it's just going to swap pairs of numbers. And hopefully by the time it's finished going through the deck, there'll be lots of different swaps happening. And then we will eventually have something that looks like it's a bit shuffled. So it looks like it's a bit randomized. I have a typo somewhere. What's the variable deck size? I can't see it in the function. I should have been using current deck size there. It's behind me. Okay, so let's see this working, where what we're going to do is when we do shuffle, we're calling swap multiple times. And so this is our first instance of us using a function inside another function. So if, for example, and so people are asking about ordering of things and putting all of these functions up above the main instead of just these declarations of the functions here. The beauty of having all of those declarations up there is even though shuffle uses swap, I could put shuffle up here. Actually, I'm not going to put it up there. I'll just put it above swap. So now I have the swap function below the shuffle function, even though the shuffle function wants to use swap. So if I didn't have those declarations at the beginning, I wouldn't be able to do this because shuffle wouldn't know what swap is. So the beauty of saying, okay, here are all my functions before I do anything, means that I don't care what order the functions are down here. So swap's here, shuffle's here, print is here, and read is here. It doesn't matter what order I put the functions in down here because they all know what each other is. If any of them use each other, they don't have to know in advance. They don't have to actually be above or below each other in the ordering down here. So me having this up here means I'm not limited, and I don't have to be really careful about the order that I do the functions there, as in which order one calls the other or anything like that. Because this can get really complicated when you have multiple functions all calling each other. Okay, so here's my shuffle, and I will now try to compile and run this and see if it is doing something sort of random with my deck. So I will compile shuffle, and hopefully I didn't leave any of those little errors in there, and we will run shuffle. So let's just put 5 cards in again, and I'm going to put 1, 2, 3, 4, 5 so we can see really clearly if it has done some swapping and things. 1, 2, 3, 4, 5. You know why? I know why already. This is pretty funny. I didn't actually call the function. So read input, then shuffle the deck. I've picked up a deck of cards and then put them back down. It's like I wrote all this stuff for shuffling and just didn't use it. So the deck is used there, and we type in the deck size. We give it the deck size so it knows how much it's going to shuffle. Okay, so now we should probably shuffle. Let me make sure I saved that. I've saved it, yes. Compile this, run the shuffle, and we'll do the same thing. 1, 2, 3, 4, 5 cards. All right. 1, 4, 5, 2, 3. So I've had some swapping going on. I don't know exactly how it got to there, but I know it's done some shuffling around, and I've not exactly randomized the cards that I have there. So I like that. That's good. So what we've been able to do here, and I should show you a lot of things that we're able to do here. We've written functions. In particular, we've got a function that's used pointers. So it's gone in and changed the values inside the array. And then we've got a function that called another function. And it was able to do that, even though it was before the other function. It was able to do that because it saw all of the functions there. But another thing I want to bring your attention to, this is very much a style thing. Look at my main function. My main function is able to be nearly read by someone that doesn't understand code. So if I go, okay, deck of cards, max deck size. Maybe I know something about this to say there's a deck of cards that has a maximum size. And then I say read input, shuffle, print deck. That's my main. That's all that's in my main, is like 3 functional lines of code. And yes, there are like nearly 100 lines of code here of all this other stuff going on, but you don't have to know. All you know is that we read input, shuffle, and print it back out. This is the kind of next level, how you use functions in order to make your code super readable. Oh, Shrey's asking, hey, is it a waste of code to make functions if we only call the function once? Not necessarily, because you can see here that read input and print dec have only been called once each. Shuffle's also only been called once. Swap has been called multiple times because it's inside a while loop. So what I've done here is, yes, all of these functions are only read once, which means if I wanted to, I could have put them all in the main. But instead, what I've done is I've made my main really svelte. I've made it really concise, and I've made it mostly English words, so that what my main is now is a really nice overview of what my program does. I'm going to have to stop there, because I've gone over time, but I just really wanted to make this point here. Those of you who are wanting to make code that is really easy for people to understand can do code in this multiple levels like this. So this is the easy to understand level of the code, and if you really want to know what this shuffle does, you go in here and you say, okay, here's the code for shuffle, and I know this only does one thing. It does the shuffling, but I can look at all the code in here and see exactly how the shuffling happened. So it's like, this is what's happening, and then you go into detail and you say how things are happening, and you can separate things like that, and it's really nice. And so Miguel's saying, and maybe even an answer to Shrey, if it simplifies the readability, then it's a good idea. It declutters the main function, makes it easier to follow. So yeah, I agree. That's how I like it as well. Sarvesh is saying you could swap the numbers without using pointers too, right? Yeah, you could. If we wanted to use indexes into the array, we wouldn't necessarily have to use pointers. In fact, we could do this whole thing without this function and just do some stuff with indexes in here, and it could potentially work. Yeah, but I just still wanted to use a function that had pointers in it, because I was just talking about pointers. Jay is saying if we run the program again and enter 1, 2, 3, 4, 5, we will produce this. Will we produce the same result? Yes, because this isn't random. This is exact and what we would call deterministic. Okay, I'm going to call it there because I've gone way over time now, and I really need to stop. So I'm going to call the lecture there. I'm going to end it. Thank you for coming. I'll see everyone next Tuesday. If anyone wants to stick around to get any questions answered and stuff, stick around. I'll be back in a moment. All right. Bye, all. Alright, I'm back. So, a couple of questions coming up, and just as we were finishing, Savesh had a really, really good point. Can we do this swap without pointers? We could actually quite possibly do the swap without this function entirely. So this is actually utilizing a pointer that is not a pointer. A pointer that is not a pointer. This. Knowing that an array passed into a function is the address of the array makes the pointer going in makes the array going into a function very similar to a pointer to the start of the array, which means that we get access to all the elements in the array, in which case this code here that was accessing pointers to parts of the array could be done on this and this. So let's do a thing. Int temp equals dec I. Dec I is equal to dec other card. And dec other card is equal to temp. We can put this in here just because we know that if we passed an array into this function, that was actually giving us the address in memory of that array. So we can affect that array in this function. So we could put the important part of this swap function here, and then we'd actually get away with not using another function. I haven't done that because I think that there's a possibility we might want to use this swap function somewhere else. So if I did write it like this, and I didn't write this function, let's say I delete that function, and then somewhere else in this card game I want to swap cards. So I want to say that there's a rule in the game that makes you swap a card with someone else. I've given up the chance of that functionality by embedding it here in the shuffle. This is a decision that we never really know for sure, because sometimes we want to split all our functionality apart into these different little pieces and reuse them. Sometimes that just adds clutter because we've got a million functions. Having said that, having lots of functions is usually going to be easier for you to use than having less functions. So it kind of goes either way. You could definitely, this functionally works, right? Because of the fact that this array, if we pass a whole array into a function, we get the address of the array, which means we can treat it as if we'd been given a pointer to the array and we have access to it inside our function. In fact, you can't give a whole array to something and actually have it copy in. So every time we pass an array into a function, it's kind of like we're only ever giving pointers to arrays. It's not exactly the same. There's some little subtleties involved, but you can really think of it like that. Anytime we pass a whole array into a function, we're giving the address of the array. So yes, we could put the swap in here and it would still work. It varies on what your program is going to be for, whether it definitely wants to do that or not. So it's hard to 100% decide how to split these things up. On instinct, I did split this up separately because I thought card game, swapping cards, chances are that swap could be used for other things. Oh, I just pressed Control S instead of Control Z. I was going to undo that. That's alright, I can still undo. Okay, so I'm going to undo my changes here because even though, yes, I 100% agree with you, Savesh, this can be done. I still, on instinct, still kind of want to separate this on the off chance that this gets used for other functions in this, if this program continues further. Okay. Ethan's asking, I have a question about styling for the assignment. Is it necessary for a submission to totally conform to the style checker? And Shrey's answering that already. Shrey said yes and no. You should aim to have the style checker be extremely happy, but sometimes it makes mistakes. So style checker is still not a human. It follows really exact rules, which means there's certain things it will say about variables and stuff like that that aren't exact. Someone's already pointed out to us, someone emailed us saying that one of the weird things that it does is it doesn't like you putting a negative in front of things. It tells you you should have a space between all your operators, even if you're just trying to put an expression in brackets like a plus b, and then put it in brackets, put a negative in front of it, which is like perfectly valid maths. But the style checker doesn't really like that, so it's not perfect. Sometimes it makes mistakes. If you're unsure about it, you can always talk to your tutor about it, and they will probably say, look, I can read that. That still looks like correct mathematics. I'm okay with that. But at other times, it might be like, oh, I think that you do need to listen to the style checker here, because this is the kind of issue, and this is where it might be a problem. So most of the time, the style checker's rules are really easy and correct for it to follow, but also it's just a little program. It's not like a world-spanning artificial intelligence that can decide on human understandability of different words in the context of how they're being used in code. So it's definitely not going to help you with variable names. It's not going to help you with white space between paragraphs, because when we have actually, bad example because I've separated everything into functions. I don't really have paragraphs in my code. Or maybe here, right? This is the input bit, and this is the looping bit, and so white space here makes sense. Style checker is not going to know. It's not going to know the difference about whether there should or shouldn't have been white space between different subject matter like that, because it just can't be that smart. So yeah, as you can see, some things it will be able to figure out, and some things it won't necessarily. So example Ethan has is you have multiple conditions in an if statement. The style checker is asking you to move that if statement condition into another function. Oh, because the style checker is seeing you try to do too much in one go. I don't know. Specific example, I think that would be something to talk to your tutor about and say, what do you think about this if statement? Because it's got a lot of stuff in it. So maybe the style checker is trying to remind you that too many ands and ors and questions like that in an if statement lead to your another programmer or yourself getting confused as to what exact question that if statement is asking. So it might have a point, but again, I would think that if it's going to warn you about something, that it's something to look at, but that's still, you can still assess that on like a case-by-case basis. Cecilia's asking, I'm confused about why line 58 uses and instead of star in the swap function. Line 58. Is this before I change stuff? Is this line 58? Or have I... Oh, here, line 59. It must be this one, right? Okay, so this was me being a little bit tricky. So, swap. Swap says I take a pointer and another pointer. So let me show you an example. Let me show you an example of a different function that I could use. So here's a void function called maybe it's an int function. Actually, I'll just stick to a void function called multiply, and it takes two integers, integer a and integer b. So let's just assume that this exists, because I'm not going to bother writing it. Let's assume that this exists and it's there to multiply two integers. So I have an integer x equals 100 and int y equals 50. So there's a few different ways I can call this multiply function. So I can multiply x and y. I can also multiply 25 and x. And I can also multiply y and 320. Just making up random numbers, right? Oh, sorry, Ethan. It's really funny. Your message has been held for review by YouTube because it's got so much text and symbols in it that YouTube thinks that it might be some kind of spam. We'll get to that in a second. I'll go back to yours in a second, Ethan, after I've finished with Cecilia's question here. Okay, so think about what we're doing here. Multiply takes in integers. This is an integer because it's an integer variable. This is an integer because it's the value that an integer could have. So let me also now look at the swap. So let's go integer pointer, point x is equal to the address of x, and now integer pointer point y is equal to the address of y. So if I want to, I can very much definitely take the pointers point x and point y and put them in the swap, because that's exactly what the swap function wants. Swap function wants pointers, and point x is a variable of type pointer, integer pointer. And so this thing says integer pointer. It's nearly, actually, you can nearly think about this as the star being part of the type of the variable. It's a bit weird because the star looks like it's connected to the variable here, because in a way it actually is. So the formatting looks weird to us because our types have up until this point just been a single word and separated by a space to the variable, but we can actually think of this as the type. So if the type of point x is an integer pointer, it can come in here. But in the same way as this, so x equals to 100, that type of value I can put in here. It doesn't have to be an integer variable that goes into this function. It can be a value that can fit in an integer variable. So I can do this. Because if this could be fit into this variable, then this could take the place of that variable as being something that could go into that function. This is the address of x. Point x is also the address of x. It's a variable that stores the address of x. Swap can take either one of those and still be happy. So we can take either the a created pointer, so a created and declared pointer, or it can have the thing that could be stored in a created pointer, and it can say, I can take that as the input. So Ethan's conversation there, I think Shrey and Ethan might take that one offline, because I think that's, Ethan, if I saw that, I would say I'm not sure I can fully understand what's going on in that line, but it depends on how you format it. And also, if you put a comment above that saying something really specific about it, then maybe it's okay, but it looks like a lot. Anyway, back to the question that Cecilia and someone else said, same question. Ningting had the same question as Cecilia. Are you getting the idea now that when I have a function that says I take in a certain type as input, so I take an integer, that integer could be a variable of that type, excuse me, or it could be a value that can match that variable. So for example, here I've taken in the variable type, but here I've taken in an address, which is what that variable type can store, and the function will be just as happy with either one. Yeah, so Cecilia, you're starting to get it now. Yeah, totally. The and x is also means the address of x. Yeah, so nearly to the point where every time we see this and now, every time you see and, say address instead. even with scanf, because scanf is actually saying what's the address of that memory, because I'm just about to dump some information in there, so I need to know where that memory is. So this is the address of X, this is the address of Y, and I can store the address of either of those in a pointer that is the right type. So a integer pointer, point X, can be aimed at X, and that pointer itself can go into the swap function, but the swap function, because it takes a pointer as input, can take an address as input, because an address is what the pointer stores. So it's like an integer stores a number. An integer function can take an integer variable or the number. And a pointer function can take in either the pointer itself or the address, which is what the pointer can store. Yeah, so Ningting's asking, so point X equals the address of X. They are all addresses. Yeah, a pointer, all a pointer is a variable that holds the address of a piece of memory. Cecilia's got it. Awesome. Great. Good to see. Yeah, so the pointer stores an address. So we've got an address here, which is that, that weird 0x number. We don't really want to work with those 0x numbers so much. Like every now and then we look at them, but it's like I can't really see that and memorize the number or anything. So I try not to look at them too much. But I have this pointer storing this address, which means that either of these things can go into a function that takes a pointer as input. And I think the concept is getting through there. Hopefully, yeah, both of you have got it. Awesome, good to see. Are there any other questions? Did anyone else have any questions? I should delete all this stuff before I upload it, because this is like, okay, I was so proud of my main being nice and pretty, and then I unprettied it with all of that stuff. Okay, but either way, I think that was a good example to show you at least how that kind of fits together. I'll just hang out for a second and see if there's any more questions. If there aren't any more questions, I will wrap up the lecture there. And obviously I'll upload this code. But I was really happy. I really wanted to show you this, because this is the S tier level of using functions for style. Alrighty, I think we're good for questions. Thank you all for coming along. I hope that you've learnt a little bit more about memory, and don't worry if pointers are a bit confusing. We are going to devote some time in tutorials and labs about it, and actually we're going to see them again and again and again through the rest of this course. Alright, see you all soon. See you next Tuesday. Good luck with the assignment.